Okay, take it away.
Thanks to everybody who's come back and to the new people like Preston. So yeah, so part 3, before I jump into, okay, well, wait, part 3 is going to be about the chromatic filtration, but before I jump into that, I just want to review what we did last time, just as a sort of memory prompt. So the first thing we did last time was we talked about complex and oriented theories. These were theories that had Turing classes and a formal group law, and the role in life of the formal group law was to tell you how to, so these things had Turing classes, so there was a first Turing class, and the formal group law is the rule that tells you what is the tensor product of what is the first Turing class of a tensor product in terms of the Turing classes of each of the line bundles that you're tensoring. So we talked about formal group laws, then we discussed how mu carries the universal formal group law. Okay, so any other formal group law comes from taking a map from mu to the coefficients of the other one and applying it to the formal group. Then we proceeded to define elements Vn. Okay, so for fixed, these are going to be really important today, so I'll go over the definition again. So you fixed a p, so the Vn depend on p, though it's not apparent in the notation. And Vn is going to be an element in degree 2 times p to the n minus 1, and it's defined to be the coefficients of x p to the n in the p series for mu. Okay, so it'll appear right there when you expand that p series. Remember, the p series is x plus fx p times. Okay, now that we have the Vn, we could define the height. So a formal group law, which is classified by map from mu star to the coefficients of the formal group law, then such a formal group law is going to have height less than or equal to n if the image of Vn is a unit, and it's going to have height equal to n if also all of the previous VIs go to 0. After that, we discussed the Landweber exact functor theorem. Whatever that was, it allowed us to construct new theories. One example was the Johnson-Wilson theory En, and its coefficients look like that. And it's a prototypical example of a theory that has light less than or equal to n.
Yes, now, is there a small typo in the coefficients for En? I see Vn and then Vn again.
The last one should be V.
Although, guys, technically it doesn't change it, right?
Oh yeah, you're right. That was actually correct. Well, I don't know. That's not what I meant to write. So thank you, Dan. Okay, so now the Morava-K theories were not defined using the Landweber exact functor theorem, but sort of roughly they were, you took mu, you localized the p, and then you killed all of the VIs except for Vn, and then you inverted Vn. And that's how you got Kn. And its coefficients was Fp with Vn adjoined as a unit, and it had a formal group law of height exactly n. We discussed how the K theories are somehow orthogonal. So if I take the Kn homology of Km, it's going to be 0 unless the two m and n are equal. Okay. And finally, I mentioned that if X is a finite spectrum, then the vanishing of Kn star of X implies the vanishing of Kn minus 1 star of X. And this was a theorem of Ravenel, and these things will come up again today. So important today will be the VNs, the concept of height. This guy will make small appearances, and the Morava-K theories with their properties. All right, so that's last time. Now, today, this is what I hope to cover. So far, I haven't covered everything I've hoped to cover every day, but we'll try again. Okay. So the chromatic fracture square is where we left off last time, and this is going to be covering a series of theorems, which a lot of them sort of come from conjectures that Ravenel made in his '84 paper. So that's online. It's called localization with with respect to certain periodic cohomology theories. So that was one of the seminal papers for the field, and we're going to discuss the conjectures and some of the results that were done in there, and then they were proved later on by Ravenel himself, but then also Devenotz, Hopkins, and Smith did some work on some of the stuff we're going to talk about, and many others. So now my goal for this is, so these results, these theorems, their proofs are pretty lengthy. So my goal for today is just to go through the statements of the theorems mainly and try to motivate them, but also try to get you to understand the statements so that then you can sort of have the big picture and then go navigate through the orange book to go see how these things are proved. Okay. Okay, so first, there's a definition I never made. This one should be pretty quick. So it's just the wedge of two spectra. So this will appear, already has appeared, but I never said explicitly what it was. Since it's not hard, let's do it. So you have a spectrum E, which is, I'm going to think of as a sequence, and F, another sequence of base spaces with structure maps. Then if you want to form the wedge, then what do? You take the sequence En wedge Fn, and then you take these maps, okay? So this one is the one that you get from the two structure map, and there's always a map from the wedge of the loops to the loops on the wedge, okay? That won't be a weak homotopy equivalence, but you spectrify, okay? So you turn it into a spectrum. Now this V here, it's both the product and the coproduct in the stable homotopy category. So you get stuff like the homology associated to the wedge of ENF is the direct sum of the homologies for each. And for cohomology, I see that my star got lost in my bracket, wants to be in the thing, but the cohomology of the wedge is the product of the cohomologies, which is the same as the direct sum in this case, but and so on. Okay, so let's see. Now we're ready. I've mentioned this, we're ready for the factor square. I've mentioned this ln of x before, but now we're going to like officially define it. Ln of x is the Bousfield localization of x at the wedge of k0 up to kn. Okay, so what does it do? So it takes so Bousfield localization at this wedge, it inverts sort of any map which is a k0 star isomorphism, k1 star isomorphism, all the way up to kn star isomorphism. Okay. So roughly, now this remark here is really, this is heuristic, okay? So be careful because what I'm going to say doesn't actually make sense. So roughly, well, how do you want to think about ln? Ln is like inverting Vn. But this actually doesn't make sense because what's Vn? We'll see later, we'll talk about that more later, like what are the incarnations of Vn in this story, but it can be made precise if you have an mu module spectra. So suppose like, for example, you have something like, if you have a spectrum which is mu smash x, then Vn and mu make sense, so you can talk about inverting Vn. And that's what ln does in that case, okay? Now LKN is like, you invert Vn, but then you complete at this ideal, okay? Again, doesn't really make sense, but makes sense for mu module spectra, and that's actually what it does then. Okay. So LKN is like a localization, so it's like, it is like a completion, so that's like looking at formal neighborhoods, and ln is like inverting something, so that's like looking at open sets, okay? So now now we're done with the heuristic. For every spectrum ln of x, so this localization at this wedge is the same as localizing at this Johnson-Wilson theory, and it's the same as localizing at the theory you get from MUP by inverting Vn. So let me say now, inverting Vn, so MUP, it's, so if you take, so I'm gonna let this be the degree of Vn, so it's 2 times, I guess I can be precise. So it's 2 times p to the n minus 1, MUP. So I'm gonna make a map to M, so what's this? So I'm gonna call this composite Vn. So this is, you do Vn smash the identity, and then you multiply the 2 copies, okay? So if you have a homotopy element and a ring spectrum, you can get a self-map out of it, okay? And this thing is just gonna be, okay, so this is gonna be the homotopy colimit, and we'll see that come up again. of, let me give myself more space. So Vn minus 1 of mu p is going to be the whole column of, okay, so you do mu p, and then you do Vn. I'm going to ignore the suspensions, okay? You have to put in suspensions for this to make sense, and so on, okay? So you just like, you go down this colimit, and if you think about it, like anywhere you get, so any element in this colimit, you can push it forward, and it becomes divisible by Vn. So it's like you've made everything divisible by Vn. Okay? So, all right, so then another fact that's true is that, remember these things, the Kn and the K0 up to Kn, they're like orthogonal to each other. So if you can localize something which was Lm local for m less than n, then you'll get 0, okay? So that's another piece of these orthogonalities of these localizations. So in lecture 1, I gave an exercise. It looked like it looked like there's natural transformations like so, okay? And so in this example, it gives us natural transformations from ln of x to ln minus 1 of x, because ln minus 1 is localization as localizing at a wedge sum n of what you localize for ln. And similarly, you get a map like so. Okay. And now these maps, they fit into a homotopy pullback, which is called the chromatic fracture square. Okay. And it just says that ln of x is the pullback of, so you can look at the ln minus 1 localization, the kn localization, and you glue along ln minus 1 of lkn. Okay, so what I'm going to do next is draw a picture of this pullback. So I had and if you downloaded your notes earlier, you had a picture, but I kept being unhappy with it, so I'm going to draw it live. Okay, so I'm going to, so MFGL is going to be the moduli stack of formal group laws at a prime P, okay? So whatever that is, it doesn't matter. Look, it's like the picture of like all the formal group laws over a P local ring, okay? So you've got this gadget, and it's got these open sets. So now I'm going to need different colors. So this, and then this. So what am I thinking? So the way I'm drawing, I'm thinking of the blue as everything outside this, and the green as everything outside this. Okay. So let's call the blue, let's call less than or equal to n, and then the green, sorry, n minus 1, less than or equal to n minus 1, and then the green is going to be the stuff that's less than or equal to n. Okay. Right on the boundary, you could have, there's a point which is the formal group laws, so whose height is equal to n, okay? And you want to think of this less than or equal to n stuff as the open set corresponding to en. This is the open set corresponding to en minus 1, so that's this term, that's this term, okay? And then so the stuff for, so I think I want, so the stuff for height n, well, okay, so LKN I said is like a completion, it's like a formal neighborhood. So it's like you take a formal neighborhood of like the height n stuff, and you want to think of it as this region here. Okay. So that's this part, okay? And then what is it saying? It says, okay, well, the stuff less than or equal to n is glued from the stuff less than or equal to n minus 1, a formal neighborhood along their intersection. Okay, so that's what that is. That's the picture that people will draw for you. Okay, so now you can also just prove using the properties of localization that you have a pullback, but I think the picture is especially for remembering what's in the pullback. Okay, so now so for the next little bit, I'm just going to tell you about some theorems about these localization functors. So these are theorems of Hopkins and Ravenel. So the first is the localization theorem, and sort of it captures this thing that if you're looking at mu stuff, mu modules, then ln is really inverting Vn. Okay, So first of all, for every spectrum X, I couldn't state the localization theorem without stating the whole thing, but here it goes. For every spectrum X, if you want to look at ln of X and you smash it with MUP, then that's the same as taking X and smashing with ln of MUP. Okay, so the localization kind of, so for X, it's like doing stuff to MUP really. And a consequence of this is that if X is Vn minus 1 MUP acyclic, okay, so that means that it's the homology for this theory vanishes, which is the same as En minus 1 star of X is 0, which is the same as K0, Kn minus 1 of X star is 0. Then in that case, then if you look at the MUP homology of ln of X, then it really is just invert Vn minus 1, invert Vn. Okay. So that's useful, and I'll mention the localization theorem later. It says that for MU modules, like ln is really just what you think it should be. Now, the smash product theorem tells you that ln localization is actually simple to describe as long as you know the localization of the sphere. It's just take X and smash it with it. These are called smashing localizations. And they have very nice properties, like things like they commute with direct limits, okay, direct colimits, so directed limits. Localization always commute with limit. They don't necessarily commute with colimits, and these ones do for directed systems because of this description. And finally, one of the big theorems is that for every finite spectrum X, if you look at the P localization of X, that can be recovered as the homotopy limit of the ln localization. Okay. So these are all described in the orange book. I think the proofs are chapter 8. Okay. So these are sort of the structural theorem for ln localization. But the chromatic convergence theorems so motivates the following definition, which is going to be our first instance of a chromatic filtration. Okay? People call this like the algebraic chromatic filtrations. And it says that if you have a p-local spectrum, then we're going to let the 0th piece of the filtration just be everything. So it's going to be a decreasing filtration. And then if n is bigger or equal to 1, then the nth piece of this filtration is going to be the kernel of the map from pi star of X to pi star ln minus 1 of X. So there's a map from X to ln minus 1 of X, which is the localization, and it's just a kernel on homotopy for that map. Okay. So that's the algebraic filtration. So it's defined as it's defined. The question maybe today is like, but what is it really like? What does this do? How is it related to like inverting Vn minus 1, or how this inverting Vn elements relate to these localization? So that's actually the subject of the telescope conjecture, and that's where we're going today. Okay. So first, I need to sort of cast a broader net for the Vn's. So we're going to sort of take a turn. We're going to leave the algebraic chromatic filtration here, take a turn and talk about Vn self maps, and then we'll come back at the end to this stuff. Okay. All right, so I need some definitions. So the first definition is that of a thick subcategory. So to be a thick subcategory, first you have to be a full subcategory. Okay, and it's going to be thick if it's closed under isomorphisms. So if you think about, if you're thinking, see, I'm in the stable homotopy category, but if you think about spectra, that's closed under weak equivalences. So that's what gives rise to our isomorphism in SH. Now, if you have a distinguished triangle, so a cofiber sequence, then, and if 2 of the 3 terms are in C, then so is the term. So it's closed under cofibrations. That's people often, and sometimes say cofibrations and extensions. Finally, if the wedge of 2 things is in C, then each of the terms have to be. So that's what people call closed under retracts. So that's what it means to be thick. Now, examples of thick subcategories is the category of finite spectra. And I'm going to denote, for the rest of this, I'm going to denote finite spectra with a C here. The reason, the C is for compact, okay? So I guess that sort of makes one thing of finite, and it's to be consistent with some of the literature that I'm going to point out. E-local spectra and E-acyclic spectra are thick. So checking this is, you can just think about it. This is a good exercise. And if you have a full subcategory of a thick subcategory, then you're going to be thick, okay? So that's the definition of thick subcategory. So it's just got, you know, it's closed under enough of the operations that you're interested in. Now, I could skip the next definition, but I won't because it serves well for the motivation. So a thick subcategory I, suppose you have one of these thick subcategory C, and then you look at a thick subcategory of it I. Then we're going to say that it's a thick tensor ideal if, well, it looks like an ideal. So first, the point is an I, so that's the 0 element. Okay. And it's closed under outside multiplication. So if X is an I and Y is in C, then Y times X is an I. Okay. So it's exactly what you would think for the definition of an ideal. And suppose this thing is proper. So suppose you have a proper thick tensor ideal. So I'm going to call it P because I'm about to define what it means to be prime. Then you're going to be prime if, well, exactly what you think. If the product of two things is in the ideal, then X is in P or Y is in P. So that allows you to define the prime ideals of a triangulated category which has a monoidal product, like the smash product, okay? So it's like, it allows you to define something that looks like spec C, as in spectrum in algebraic geometry, the prime spectrum. And I'm gonna direct you to Balmer's work to read more on this. So I put a link to his stuff on the website, and he sort of generalizes these, well, he talks about, he makes these definitions in a general context and puts a topology similar to the Zariski topology on this set. Okay, so when people say like something is the prime of some category, often they mean in this context. Okay. Okay, so thick tensor ideals of p-local spectra. So let's look at examples. So we're gonna fix a prime P. And for each integer bigger than 1, we're going to let Pn be those. So what is this thing? This is p-local finite spectrum. So it's finite spectra. You take finite spectra and then you p-localize. So you're going to look at those p-local finite spectra whose Kn minus 1 star homology vanishes. So it's the Kn minus 1 star acyclics. Okay. And you can go through the properties. You can check that these are thick tensor prime ideals of p-local spectra, of finite p-local spectra. Okay. Remember the C here means finite. So, okay, so now we come to like one of the big theorems in this game. So just for notations purposes, I'm gonna let P0 be this. Okay, so that's not a proper ideal. That's not a proper ideal of SHC, so I'm not gonna call it prime, but we have these inclusions. So P0, or p-local finite spectra is filtered by these categories. P0 contains P1, contains so on. Okay, so this is just the fact that if Kn star of X is 0, then so is Kn minus 1 star of X, which we mentioned before for X finite. Okay. So these inclusions, that's Ravenel. The properness, that's Mitchell. So he constructed examples that were in like say Pn, but not in Pn plus 1. Okay. And the part that's Hopkins and Smith is the big theorem. So it's this sentence, and that's called the thick subcategory theorem. And it says that if you have a thick subcategory of p-local finite spectra, then it's one of these that was on your list. Okay, so it completely classifies the thick subcategories of p-local finite spectra. Yeah. But these Pn here, they're prime ideals. So you'll hear people say things like Kns are the primes of spectra. And that's why, okay? Because of the thick subcategory theorem. It classifies the thick subcategory, and they're all prime ideals. So that's it. That's what the prime ideals have to be. All right, so now we're ready for one of the important definitions for today. Well, there's been a lot, but the next one. So we're going to say a finite p-local spectra. We're going to say that it has type n. So when I say type n, I always mean finite. Okay. So what is that going to be? It's going to be a spectrum that's in Pn, but not in Pn plus 1. So in other words, you need to have that Kn star of x is not 0, but Kn minus 1 star of x is 0. Okay. If you're confused by the index shift, it comes from, it comes from here. Okay. All right, so examples are, so S naught P, the P local sphere has type 0. K naught star, that's HQ. That's rationalization, it's not 0, has non-zero homotopy in pi naught. So S mod P, so if you don't remember what that was, so that's the cofiber. So one way to think about it, it's the cofiber of the multiplication by P map. That has type 1. So the rationalization is 0. But K1 star of S naught P is not 0, and you can just use this distinguished triangle. So distinguished triangles give long exact sequence on homology, so you can just use this to see that K1 star of S naught P, of S Z mod P is not 0. So these are a prototypical example of a type 0 and a type 1 spectrum. Okay. So I didn't know I had 27 slides. Okay, so I thought I had 18. Okay, so you use the exercise that I'm gonna sort of assign to you if you want to do it, and that's gonna come up later, is that now that we have the definition of a type n spectrum, just from the definition I gave, you can use the chromatic fracture square, which we introduced earlier, to show that in the case of type n spectra, Ln localization is the same as Lkn localization. Okay, so Ln localization was supposed to like invert Vn, and this was supposed to invert Vn n complete at P up to Vn minus 1. Well, these are all kind of like, so I'm gonna, this is all in quotes, but this is like 0 on type n spectra. So completing at the 0 ideals like do nothing. So for type n spectra, these things are the same. And okay, so one of the big theorems of the field, and note this, I'm doing things out of order. The nilpotence, the theorem I'm about to state comes before the theorems I stated on the previous page, but for presentation I chose this order. So the theorem says that, okay, so if you have a self map, which is a map from sudden suspension of x to itself, so you can look at fk, which is the iterates of this self map. So you do f, and then you do it again. You do f, then you do it again, and so on. You do it k times. And if for some k this is null, then we say that f is nilpotent. Okay. And one of the sort of breakthrough theorems in this field is the nilpotence theorems by these three. And it says that if you have a spectrum in which is finite and p local, then a self map is nilpotent if and only if its Morava K theories vanish for all n. Okay. So if you were wondering like why do you care about the Morava K theories, well, questions like which maps are nilpotent, these are classical questions in our field, and having the Morava K theories at hand is a test for checking for nilpotence. All right, so now that we have type n spectra, we need to talk about Vn self maps. So remember I said let's put more context to this Vn, and this is going to happen now. So if n is greater or equal to 0, we're going to say, okay, sorry, I wanted to say something before. I'm going to use the following definition for Vn self map. You can make a slightly more general definition. The place to look for this stuff is called Nilpotence 2. It's the paper by Hopkins and Smith. It's a beautiful paper. But I'm going to use the same definition that Ravenel does in the orange book. So here we go. So you have n bigger than 0. We're going to say that a Vn self-map for x is a self-map, and it has the property that it's 0 if n is not m, and it's multiplication by some prime power of Vn if n is equal to m. So for example, if you look at the p multiplication on the p local sphere, that's a V0 self-map because V0 is p, okay? So if you check, so for bigger than 0 multiplication by, for n bigger than 0 multiplication by p is 0, and for p is 0, it's multiplication by p on the rational, which is multiplication by v0. Okay. Now for p odd, so the Adams map. So what do I mean by the Adams map? I don't have the time to explain what they are, but this is the maps that Adam constructs in J of x4. Okay. So these come from the story, the image of J story. Okay. But they're maps from, so if p is odd, they're mapped from the suspension time of 2p minus 1 of the mod p sphere to itself. Okay. And one can check that this is a V1 self-map, and K1 star of alpha is V1, multiplication by V1. For p is equal to 2, the story is a little bit more complicated. So there is an Adams map, but it goes from the 8th suspension of S Z mod 2. Remember, so note that that's not equal to 2 times 2 minus 1, right? So that's 4 times that. But it's still a V1 self-map, and K1 star of alpha is V1 to the 4. Okay, so here I didn't ask for this thing to be 1, just some power. Okay. So these are the classical prototypical examples of Vn self-maps. Okay. So now the periodicity theorem of Hopkins and Smith says that, so it's a finite spectrum, has type n, if and only if it has a Vn self-map. Okay. So ways to detect type n spectra is to look at the K and star homology. So you compute K and star of x. Remember, K and star has a Kunith isomorphism. It might not be so hard to compute it. So you compute K and star of x, and then maybe you notice that Kn star of x is not 0, but Kn minus 1 star of x is 0. And the periodicity theorem gives you something extremely strong. It says, well, in this case, that's all you knew. You have a self-map. You have a map here that on Kn star homology is very predictable. Okay, and in any other case, you don't have such a thing. So furthermore, so they prove something else in this paper. They prove that Vn self-maps are essentially unique. Okay, so in the sense that there are different choices, but they don't differ that much in the sense that if you have 2 of these, maybe they're different, but if you iterate them, so you take powers of both, eventually they're the same thing for I and j is bigger than 0. So because of this, I'm going to treat them as unique. So because if you just like their self-map, they induce isomorphism on K star homology. So you want to think of them as like periodic operators, okay? And you have one operator, the other one. If you iterate them, they become the same, and it doesn't really matter how many times you iterate because they're kind of periodic things, okay? So for us, I'm gonna pretend like any choice doesn't matter, because at the end of the day, because of this theorem, you can always sort of do away with the dependency on choices for the constructions that we're gonna do. So now here's a fun exercise to test that you an excuse to go over the definitions and try to understand them. So suppose you have a type n spectrum and you have its self-map that's given to you by the periodicity theorem. Then you can look at the cofiber. So there's a distinguished triangle like so. Okay? And then the cofiber here actually is going to have type n plus 1. So in particular, it's going to have a Vn plus 1 self-map. Okay? And the hand, this is a pretty straightforward exercise. It's also in the orange book, so that you can find the proof in the orange book somewhere. But what do? You just, you have this exact triangle, so you can look at the long exact sequence for the various K star homology and use the properties of the Vn self-map to prove that CF has type n plus 1. Okay. All right, so if I have a VN self-map, I can produce, so if I have if I have a type N spectrum and I have chosen a VN self-map, I can produce a type N+1 spectrum out of it. So in some sense, this exercise is a machine for producing type N spectra out of old, okay? So let's see that in action. So let's talk about constructing type N spectra. So suppose that X has type N and it has a VN self-map. Then CF has type N+1. That's just a sentence I wrote. I just rewrote here so you can look at it, okay? So here are the examples. So if you look at multiplication by P on the P local sphere, the co-fiber is this S Z mod P, and we already saw that it has type 1. Okay? Now, we call this M1 sometimes. It has a lot of names. I'm gonna not name all of them, but sometimes it's called M1, and it's because P is V0 to the 1. That's the 1 here, okay? So for P odd, we had our self map. So this was the Adams map. Here I wrote this was S Z mod P on the previous slide, okay? And K1 star is V1, so the co-fiber has type 2, and we call it M11, and it's because this is V1 to the 1. Okay. For P is equal to 2, the Adams map again satisfied this. So the co-fiber, that was a V1 self-map, so the co-fiber has type 2, and it's called M14, and that's the 4. Okay. So in general, suppose that you, in general, what's going to be Mi0 up to In? Well, it's going to be the type N+1 spectrum, which is defined inductively as a co-fiber. So suppose you've constructed Mi0 up to In-1, and you had a Vn self-map, Fn, and it had the property that Kn star of Fn was Vn to the, here's the In here, then you call the co-fiber Mi0 up to In. So there's no, these things, these Mi0 and In are not unique, okay? So it does depend on your choices, but I'm just gonna ignore that. I'm just saying you can construct these. There's a machine to do it. Now, if it exists, M11111, if you can always pick one, that's called a Smith-Tota complex. And on my web page, there's a paper of Nave, which talks about non-existence of certain Smith-Tota complex, and in there, I believe he covers some of the background of like when do these things exist and when they don't. So for example, at P is equal to 2, M11 does not exist. Okay, so here we had M14, not M11. So that's a difficult question of when Smith-Tota complex exists or not. All right, but in any case, we're going to be using these guys, okay? So remember what this means. I'll keep repeating it, but that's going to be, so this is going to be important in the next couple slides. Okay, so now we're ready to talk about periodicity. So chromatic homotopy theory, you've probably heard like, oh, it's these periodic families, okay? Well, here it goes. What does that mean? So I'm going to write, just on this slide, I'm just going to shorthand Mn for Mi0 up to In-1. So it's a type N complex with a Vn self-map, which I'm going to call Fn. And then we're going to say that Kn star of F is Vn to the In. Okay? So I'm not fixing them in advance. I'm just saying like whenever I write, that's the notation that I'm using. So now suppose I have a P local spectrum. And I have an element in its homotopy groups, okay? So that's a map from SR to X, which I'm gonna also think as a map from S0 to sigma minus R of X. And I just realized my knots are on there and wrong. Now, so we're gonna find what it means to be N-1 torsion, but let's look at, so it's gonna be like the existence of certain factorization, but I'm gonna go through them with you, okay? So first you have this, map here. That's your homotopy element, omega. Then suppose omega is P torsion, then F0 here, that's some power of P, right? So that's P to the I0, okay? So if this map here, if this composite is 0, so if it's null homotopic, then you can look, so here, this thing here, that's a cofiber sequence. So if the top composite is 0, then it extends to here. So to M1, which is a type 1 spectrum, so it has a V1 self-map. Okay. And again, if you can find a power of a V1 self-map such that this composite, so this map is 0, then it extends over the cofiber. So this is a cofiber sequence, I guess if I had M2, and it keeps going. Okay. So you can assume that, suppose you've extended, so W to a type n-1 spectrum, you can precompose with a V1 self-map. And if for some V1 self-map, this is 0, then you can extend over the cofiber here, okay? And I'll call this Wn. So we're gonna say that something has Vn-1 torsion if you can iterate this process up till stage n, okay? Now, I didn't say anything about the last map here. I didn't say anything about this. So if you want to keep further, then you're going to precompose with Vn self-maps Fn and check whether or not you can get a 0 composite, okay? If you can't, so if this is 0 for any Vn self-map of Mn, then we say that W is Vn periodic. Okay? And that's how you decide if an element is torsion or periodic. So this leads us to the second chromatic filtration. And so again, we're going to let the first step be everything in the homotopy groups of X. And if n is bigger or equal to 1, we're going to let this be the subgroup of all elements which are Vn torsion. Sorry, Vn-1 torsion. There's a shift in the index. So again, this is a decreasing filtration. And one of the next goal is going to be, well, okay, so now we have 2 filtrations on the homotopy groups of homotopy groups of X. What's the difference? Are they the same? And the answer is, we don't know if they're the same. Okay, that's the telescope conjecture. The question of whether or not these 2 filtrations that we got are the same, that's part of that conjecture. Okay, but we'll come back later. So the next thing I want to do is, so I want to sort of put context in to something that you probably hear if you're sort of at talks in chromatic homotopy theory. You'll hear about something that people call Vn periodic families. Okay, and I want to sort of tell you how this happens, what this is. So I'm gonna highlight this part of the diagram. Okay, so that's going to appear. So I'm going to sort of look at an element omega, and I'm going to assume that we can get to this end stage here, but that we're Vn periodic for this omega. So we can get no further. So that's good. This piece of the diagram is going to appear on the next page. Okay, so it's here. Okay. All right. So again, I've got my omega, and I assume that it's Vn periodic. So I went all the way to n, and in the slide, just to avoid multiple indices, I'm going to just call n mn. So we get to that n stage, and we have a Vn self-map Fn. So we have that for any Vn self-map, this composite here is non-trivial. That's what it means to be periodic. Okay. Now, okay, so M is, so it's a CW spectrum. So if you don't know what that is, just think CW complex, okay? Just think CW complex in spectra, and you'll be just fine. Okay. So it has an art skeleton, which I'm going to call M upper R. And the R-1 skeleton goes into the art skeleton, and I'm going to call the cofiber M with R superscript and lower-script. And similarly, if you put the R-1 skeleton into R, I'm going to just call that M sub R. So that's like M R dim M, whatever the dim is. Sorry, I didn't define that, so let's just stick to that. Okay. All right, so now, so this is discussed in Ravenel, okay? So you can show that if you have this situation that we're in, here, then you can produce a diagram like this. So you look at this composite here, okay? Then there's some R, so some skeleton where you can form the following thing. You can look at the map. So this is the map from M to the quotient, okay? So M modulo it's R minus 1 skeleton, so that's given by this map. Then I can include the thing where I take the R skeleton and I quotient by the R minus 1 skeleton into there. And for the R guys, this is going to be a sphere, okay? And there's going to be some R where this thing extends to a map G and such that this composite here is not trivial, okay? So there's a situation like that such that this composite is not trivial. And the lingo for this, it's that this map, Wn composed with Fn, is non-trivial on some cell of M, okay? So there's a cell that detects it. And so you don't know which cell it is. It could be the bottom cell. It could be some cell in the middle. You just don't know. You don't know, but there's going to be one that's not trivial. And for such element, then this composite, you get a new element, right? You have a map from now an SK to sigma minus R of X, which is an element in pi k plus R of X. So it's a new element in the homotopy groups of X. And we say that this element is part of the Vn periodic family for W. Okay, so it's like it's a bit of a tricky process to make this definition. You have to play with fibers and cofibers, but basically you want to think of this Vn here, you want to think of this as like Vn multiplication in a place where you can't Vn multiply. You can't, like for a general X, you can't Vn multiply, but this is the process. Okay, so you have to sort of work a little bit harder to define what it means. Okay, so now I'm going to show you some charts. So the picture you might recognize from Hatcher, the computation, it's a picture of a computation by your dog, Ravenel. And the edits I'm going to show you are mostly done by Mark Behrens. Okay, so in this picture, Z sub 5, okay, so this is Z mod 5. I think I made this picture for a more general audience, okay? Okay, so one dot here is just a Z mod 5. So you have like here, down there, here you have pi star of the 5 local sphere, and a dot is a copy of Z mod 5. 2 dot connected by a line is a Z mod 5 squared, and so on, okay? So now in the bottom line, you'll recognize the image of J. So these highlights are Mark's highlights, Mark Behrens' highlights. So in the bottom here, you have the image of J, and that's the V1 periodic families. Okay, so that's the V1 periodic stuff, and the period is always a multiple of 2 times p minus 1 because that's the degree of V1. Now Mark tells us that here's the V2 periodic stuff. So Mark's the expert on this kind of business, and he's sort of identifying the picture for us, the V2 periodic elements. Okay, so so you can see here. Yeah.
See, outside of the V1 periodic stuff at the bottom, I see very little that's except for 5 torsion. Is there sort of like a reason to expect? I mean, I guess I see a few like Zmod 25s, but not many. Is there a reason to?
Oh, yeah. I honestly don't know. I know very little about the homotopy
Okay.
of at 5. Yeah.
Okay.
The reason I'm using that one is because Mark made the picture.
Okay. All right.
Yeah. So yeah. So that's the V2 periodic stuff, and then Mark says that this is part of the V3 periodic family. Okay. So I think this part is conjectural, but I'm not 100% sure. Okay. So, but roughly that gives you an idea. So because we don't have that much data, like,
question.
Yeah.
Sorry.
Yeah. Can you explain for me a little bit more about the large part of the diagram? I understand what's happening on the bottom line, but I mean, what am I even looking at?
Well, you've got like, so I guess they're like kind of, you've got these little squares here, right?
Yeah.
And so on. So So what you're looking at is you take this element and then you look at what's this periodic family. So you do the game I played on this slide. You look at, you know, you look at, so it's supposed to be V2 periodic. So I'll have a type 2 spectrum in this picture. And then you look at which cells it extends to, and then you do this composite here, and then and then you can repeat. You can take F and you can take F squared, F cubed, F to the fourth, and you can repeat this process, and you get a family of elements in pi k plus r, which people call the VN periodic family. So what he's highlighting the repeats.
Okay.
Okay.
Did that answer the question?
Yep.
Okay. And look, I think like these are repeats of this, but then the period is longer. Okay, so you need to choose like, you know, I said like you pick a VN self-map. There's VN self-maps. There's a choice. It could be that it's not like a VN self-map that looks like multiplication by VN. It could look like VN to the P or VN to the P squared or something like that. Okay, so depending on which power of VN you have to put in there, the periods might be longer, but they're all part of that sort of periodic pattern. Okay, so that's that. That's the pictures. Now here, this is an illustration by Dan of the homotopy groups of the 2 local sphere. And it's done by, this is a picture of the atoms spectral sequence. So it's like a machine that computes these. And I think that, I think this is an old picture because I think this part is all resolved now. But in any case, in this kind of picture, if you want, you can see, so I'll go to the next slide. So in the purple here, you can see this is sort of the V1 periodic quadrant. So the atom spectral sequence sort of splits the periodic patterns into different sort of sectors, and it creates like this ray of light, which is aesthetically pleasing. So this is like the V1 periodic stuff. So you'd expect to see the V2 periodic stuff in this region and V3 and so on. Okay, and the slope are given by the degree of, so 1 over the degree of Vn. Okay, and one of my slopes is wrong. At some point, Jolie was looking at my picture and he was like, of course, it had to be Jolie Shu who was like, yes, your slope's wrong. And I was like, oh, it took me so long to make this picture. So anyway, so don't take it at face value.
Can I make just one quick comment about this? You know, it's sort of clearly, you can see clearly how like the V1 periodic stuff like pulls away from the rest and there's this huge gap, right? But we've never actually seen the V2 periodic stuff really kind of pull away from the rest of the diagram. I've always kind of been curious about that. That's not a question, I'm just making a comment since you're drawing the picture. Even at the very, very limits of what we've studied, we've never really seen that sort of another gap in there.
Yeah, so Dan speaking, like Dan has the biggest pictures we have for these kinds of things. And if you, and he's talking about if he looks at all the data that he's discovered, he still doesn't really see this sort of empty space for V2 period, between the V2 and the V3 periodic stuff. That's what you were saying, Dan, right?
Yeah, yes, that's right.
So anyways, so really cool stuff. So now let me see. I'll stop on time, but I'll try to get as far as I can in this stuff, and I'll pick up where I left next time. So let's talk about, so we've got these periodic families and these periodic things, but they're related to these Bell's-Field localization story we've given before. So I've talked about this for Vn minus 1 mu before. So now let's make the definition more generally. If you have a self-map, then the telescope of F is going to be this homotopy colimit. So you just iterate it. And algebraically, you want to think of this as having the effect of really inverting F on X. Okay? So now let's pick one of these MNs. It doesn't matter which one. And we have a self-map Fn. Doesn't really matter which one. I'm going to call tel n just the telescope of one of these type n spectrum for that periodic map. Okay. And so we've defined ln, but we haven't defined lnf here. So the superscript is the important part. So that means that stands for finite. Okay. So because, and the finite comes, these are finite spectra. The MN are finite spectra. Okay. So the definition of lnf is very similar to ln, but you localize at the wedge of these localization of these telescopes, tel 0 up to tel n. Okay. And if X happens to be a type n complex, then this is exactly what you would want it to do. It just has the effects on X of choosing a VN self-map, doesn't matter which one, and inverting it. So you get the same result no matter what choice you make, okay? So this is the telescope. So this is called a telescoping localization. Is it telescoping localization? I'm gonna go with telescoping localization, okay? Okay, because when you look at certain complex, it does exactly what you think. It takes the thing and gives the telescope. And so if we look at this geometric chromatic filtration that we defined earlier, then if you look at, so we had that's the 0th term was everything. And for n greater or equal to 1, you can also define the geometric chromatic filtration as the kernel of the map from the homotopy of X to the homotopy of the telescopic localization. Okay, so now that looks a lot like our algebraic chromatic filtration that we had before. Okay, so here's the algebraic chromatic filtration. I just copy pasted the definition from before. So the A, you might have caught on, is for algebraic, and the G is for geometric. And then we have this other localization, which is defined in terms of these finite localization or telescopic localization. Oops, sorry. Like so, okay. And so it turns out you can construct, so if I have time, which I don't think I will, but you can construct a natural transformation from the telescopic localization to just this ln localization that we defined before, okay? It's actually pretty easy to understand if X is type n, but for now, let me state that there's one. There's always a map from one to the other. And it's known to be an equivalence if X is any EM local spectra for n bigger or equal to 0. So if X looks like, if X looks like LMX for some M. And it's also known to hold if X is an MU module spectra. So this was sort of this was part of the concept of the localization theorem. Okay, that it does what you think it does on it. That ln, this one without the f, does what you think it does on MU module spectra. So that the question is, okay, so it's true in all those cases, but what about the other cases? Is it always the same thing? So in particular, can you describe this localization, which is sort of in terms of these Morava-K theories? So the localization from the Morava-K theories in terms of these more sort of geometric hands-on kind of inverting elements construction. So the telescope conjecture is the conjecture that this is always true, that for any spectrum, these localizations are the same. That's a conjecture that was made by Ravenel. He also made the other conjecture, which is the telescope conjecture is false. So Ravenel is responsible for both conjectures that this is true and this is not false. I think Ravenel thinks it's false. And he has a very elaborate sketch of a proof with Mahold and Schick. So I think that the general belief is that it's false, but there's no complete proof out there. However, if you look at the data, I mean, why did Ravenel make the conjecture? Is because at first it looked true, right? If n is equal to 0 and p is any prime, then this is true, and it's just a tautology. You're looking at exactly the same localizations. If n is equal to 1 and p is bigger than 2, this is a difficult theorem of Haynes-Miller. If n is equal to 1 and p is equal to 2, it's a difficult theorem of Mahold. And if n is bigger than 1 and p is greater than 2, it's open, although there's attempts at disprove from Ravenel. Okay. And I'll say one thing and then I'll stop. So here's equivalent formulations of the conjecture. So suppose you were trying to prove the telescope conjecture inductively, then the inductive step is equivalent to just finding one example where this holds. Okay, so you just have to find one type n spectrum where the telescope conjecture holds, and it implies it for everything. And so these are called thick subcategory arguments. Okay, so if you can prove it for one guy, you have it for all. Okay, So challenge, find a type 2 spectrum where it's true or where it's false. It'll solve the problem for you. Okay, so I will skip this slide. Next time we'll talk about the chromatic fracture square more. We'll discuss this gluing data here, and we'll discuss the building block, and this will lead us to generalization of P-complete K-theories and Adams operations and computational tools in this story. Okay, so thank you. That's all for today.
Okay, I'm going to unmute everyone so we can thank her. Okay. And I will then go ahead and mute everyone again just to cut down on the background. Okay, and we can open up for questions. Yeah, it looks like Ong Lee, do you have a question?
Yes, I have a question. So Anis, I think you talk about the Smith total complex, and that's not unique, and self-map is unique. And I think you also talk about when they do not exist, but I was wondering, when they exist, can I expect something uniqueness or a universal one?
So I guess the answer is I don't know. Like for example, I know of type 2. So if you take the Moore space, or there's like certain type 2 complexes that have different V1 self maps, and if you pick different V1 self maps, you get different cofibers, different homotopy types for the cofibers.
Okay.
So I know of examples where you know the process won't give you. But those have more than. You know what? I'm gonna. So I think okay. So let me find the slide where this was.
I think it's number 14-ish.
Okay, so we have this slide, right?
Yes.
Okay, so I'm going to correct myself. So I think what I wanted to say is that the CF here. Sorry, if you have a type 2 complex here, and you take the cofiber, then so you have a type N complex, and then the cofiber, the homotopy pair of the cofiber might depend on the choice of the N self map.
Okay, gotcha.
So non-uniqueness in general, and the examples I'm thinking of are examples that actually don't arise in this fashion. Like, so they like the X you'll choose has like, so these things only have like, you know, you add one cell at a time. These X have more cell for the non-uniqueness. So now I said, so I don't know if these MI0, if you pick the VN self map, if the cofiber then will be unique. I realized that for this case, I don't know. So then I, in particular, don't know about your Smith-Toda complex. It could be that you have something better. So I'm going to invite Prasit to answer the question if he knows if there's uniqueness for these guys and Smith-Toda complex given their existence. So he doesn't have to talk, but if he knows, he can talk.
I think in general you shouldn't expect them to be unique, but because they are defined by what is BT homology looks like. But you know, like there are examples like A1. There is more spectra smash CP2, where there are 4 different one periodic V1 self map, and all of them different cofibers. So they are all type 2 complex. Looks very similar, but they are different homotopy type. So
yeah, but Prasid, this is like an example with more cells. So what if you just do the MIs, the MIJs, like that? There's less cells to play with, right?
yeah, in general, one shouldn't expect them to be unique. I don't know. Like there aren't that many known examples of more generalized spectra for us to determine. Yeah.
Okay, thanks.
Looks like the IU Bloomington group has a question also.
Yeah, I was wondering, going back to the geometric filtration, is it obvious that this filtration converges?
I don't think so. I don't think it's obvious. I don't know the answer. Yeah. I don't know if it converges.
Thank you.
Other questions?
I have a question. So it's curious. I mean, I should really read the Orange Book at this point carefully, chapter 8. But ln is same as lnf. Is there a particular philosophical reason why this happens and doesn't happen for kn localization? Like this?
Well, I mean, no, ln. So ln and lnf are that's the telescope conjecture. We don't know if they're the same.
Oh, okay, yeah. But at some point you had something about. Okay, that's the telescope.
Which you need slide? Which slide? So
At some point you said, maybe I misread. Yeah, ln and lnf may not be the same. Oh, maybe you were concluding it for something. Okay, never mind. But I have another question though. Oh, that's the okay. I have earlier when you defined Vn self-map, you said you put the power as Vn to the p to the n, but you took it from Ravenel's book, and in Nilpotent's paper it is Vn times m times p to the n. So it doesn't really say that you would have a Vn to the p to the n necessarily. It could be some other integers, which is a power of p, which is a multiple of Vn.
you're talking about this slide where I define the Vn self-maps.
Yeah, yeah.
So what I'm using here is you look at
That
in nilpotence, nilpotence 2,
Yeah.
theorem 9, it proves that any type n spectrum admits a self-map where this is actually a power of p to the n. So I sort of like mix the definition with the theorem in my definition there.
Okay, there is always okay. I see.
That is actually a power. Yeah.
Okay, okay. So
So
that's
look at theorem 9 of nilpotence 2. These kinds of parts of nilpotence 2, if you assume the fixed subcategory theorem, the proofs are actually like really beautiful. This paper is super readable. If you just are willing to like take for granted the nilpotence 1 paper, then I hope that after this course you can go through it and sort of sort out a lot of stuff.
yeah. At some point, someone pointed out that like it is mandatory for me to put an if you look at kn star of f is equal to, and then vn to the m times p to the n is sort of should be the right thing to say. I'm just being annoying at this point by just pointing a very trivial point, but I just wanted to clarify.
No, I'm just saying there exists one where it's a power of p to the n. If you have your vn to n times p to the n,
or some k times p to the n, then
I don't know. Look at I mean right now I don't have the details of the.
I just thought that since you looked at two different definitions, you figured out something. Just curious.
I'm just saying that there for any type n spectrum, there's gonna be one that's that. And like I said, like this was this bar, right? This is not necessarily like so you might want to go and follow up on definitions and press it. I mean, you know more than I do on Vn self maps. But I mean, but I have at some point understood all the details in the proof of this theorem in the nilpotence paper that says that if you have a Vn self map, there's one that's a power of p times of Vn. There is one self map out there that has this property.
Okay.
Yeah. So but I'm not gonna I think if we want to keep arguing, we should both like after we can look at theorem 9 and look at.
No, I was just curious if you saw something.
No, there's nothing. There's nothing that I know that you don't know.
That may not be true, but anyway.
Okay, other questions? All right, I'm going to unmute everyone so we can thank her one last time.
Yeah, I guess the question.
Everyone, we'll see you on Thursday for the last talk.